The other concept we see in this chapter is singular value decomposition, or representation of image using singular value decomposition. We represent images using a matrix, a single matrix. It's possible to change that matrix into a form of products. So singular value decomposition method can transform a matrix A into a product, 3 products, which are called column orthonormal, diagonal, and row orthonormal vectors. These are 3 vectors or 3 matrices. So this allows us to refactor a digital image in 3 matrices. So the use of singular values of such refactoring allows us to represent the image with a smaller set of values, which can preserve useful features of the original image, but use less storage space in the memory and achieve mainly image compression process. So singular value decomposition allows us to decompose images into different matrices, and by doing that it's possible to do image compression. So one important application of singular value decomposition is image decomposition, image compression. So any matrix or any real M by N matrix A can be represented by a set of matrices, a product of matrices U, D, and V. So U can represent the column orthonormals, orthonormal vectors, the product of U transpose and U will be identity matrix. These are called orthonormals. The other is diagonal, the diagonal values. The diagonal values D represent the singular values or unique values. The singular values are assumed to be greater than 0. The other is the row orthonormal values N by N, and these are orthonormal. That means the transpose and itself, or the product of transpose and itself, will result identity matrix. So a matrix A can be decomposed into U, into D, and V, and the product of this orthonormal U, diagonal D, and V transpose will give us A. By doing that, it's possible to discard less important values and extract important values. So if the column and the rows are the same, the vector A will be equivalent to U, D, V transpose, and U will be N by N, D will be also N by N, and V will be also N by N, N by N. The 2 columns of U will be eigenvectors of A matrix A times its transpose, eigenvectors. So if you use the eigenvectors, A transpose A will be equivalent to this is A, transpose of this will result this one, and the product of this will be equivalent to U diagonal square times U transpose. The columns of V are also eigenvectors of A transpose times A. You see the difference? The columns of U are a transpose of A, a product of A times transpose, whereas the columns of V are eigenvectors of A transpose times A. In this case, this will be A transpose, this will be A, and the product will provide us V diagonal square times V transpose. You see the difference? This can be represented using only the U, eigenvectors of U. This is represented using only eigenvectors of V. So if lambda is an eigenvalue of A transpose A, then the lambda value will represent the diagonal square. or diagonal vectors or eigenvectors. As an example, consider this matrix, this image. So by using this equation, this is the general equation to do singular value decomposition on a matrix. So decomposing a matrix into a singular value means decomposing it into three matrices: diagonals, diagonal values, the column values, and the row values. So by using this equation, they can be decomposed into these matrices. This can be done using Matlab built-in function easily. So a square n by n matrix A is singular if and only if at least one of its singular values is 0. So the rank of a matrix A will be equal to the number of non-singular values of the eigenvector. So the matrix condition for a singular value decomposition is the condition of A measures the degree of singularity of A, degree of singularity. So the degree of singularity is equivalent to the ratio of the largest singular value to its smallest singular value. The singular values are the diagonals. So the largest singular value to the smallest singular value gives us the condition of measure of singularity. Matrices with large condition number are called ill-conditioned. It's possible also to compute an inverse of a matrix A using singular value decomposition easily without doing a complex mathematics. So if A is n by n non-singular matrix, then its inverse can be computed using this equation. We can decompose a matrix A into singular values, and applying inverse on this matrix means applying inverse on this. So only since V and U are orthonormal, only the diagonal will be reversed. So the diagonal, the inverse of A, matrix A, will be equivalent to V times diagonal inverse times U transpose T. So originally A was U D times V transpose. So the inverse of this U is U transpose, the inverse of V transpose is V, and the inverse of diagonal can be calculated using this equation. So calculating the inverse of the diagonal is very easy. So if A is singular or ill conditions, you can use singular value decomposition to approximate its inverse as follows. We can implement singular value decomposition using Matlab easily. There is a built-in function called SVD. So the singular value decomposition of a matrix A returns 3 singular matrices. If you just give one value to a singular value decomposition built-in function, it will return the singular values of a matrix A in descending order. But if you provide it with 3 inputs, the singular value decomposition of A will perform the singular value decomposition for the column orthonormal, for V, and for the diagonal. There is a way also to do economic singular value decomposition using this built-in function. So this produces an economy size decomposition of M by N matrix A for the lowest number of pixels only. So if M is greater than N, only the first n columns of U will be computed, and the S will be N by N with the lowest number of pixels. If the column and the rows are the same, the economic singular value decomposition of a matrix A will be equivalent to the standard singular value decomposition of A. If m is less than n, only the first m columns of V will be computed and S will be m by n. M by n. This is the economic singular value decomposition of a matrix. For the following matrix, determine the singular value decomposition of a matrix A using the equation. From the decomposed values, confirm the relation A is equivalent to U S V transpose. And also find the economic singular value decomposition of A. You can do it using Matlab. We can apply singular value decomposition for noise reduction purpose. In digital signal processing, we can apply singular value decomposition for noise reduction. We can do it also for image analysis or image processing. So the central idea behind noise reduction in singular value decomposition is, let a matrix A represents the noisy signal. We compute the singular value decomposition, and by discarding the smaller singular values of A and preserving the larger singular values, it's possible to reduce noise, assuming that the smaller singular values are the noises. So it can be shown that the smaller singular values mainly represent the noise, and the rank K matrix AK represents the filtered signal with less noise. So this will be your first assignment. You will do it using Matlab. Given an image A, you are asked to write a Matlab code that resizes the image by a factor of 2. It prompts the user to enter 2 pointers or pixels in the image and calculate the Euclidean, city block, and chessport distances. And then apply the economy singular value decomposition and reconstruct and display the decomposition. So there are built-in functions in Matlab. You can do your own code also and do all of the 3 exercises. The submission dates for this first assignment will be announced on the course website. Alright, the next class will be image enhancement spatial domain. So we'll try to see also the basic or fundamentals of image enhancement in spatial domain, and we'll see the different kinds of operations that are performed to enhance an image in spatial domain. So stay safe and well. ራሳችሁን ጠብቁ. Ciao.